One of the most popular control methods in electronics is, without a doubt, PWM. But what is PWM? PWM means pulse width modulation. It's a technique where we modulate the width of a square wave signal to control the on-time duration. PWM is conformed by the following parameters. The first parameter is the operating frequency. This is the time that is from the beginning of the cycle up to the end of the cycle. The frequency of the operation will vary in function of the generator and also of the load we will control. We usually work on frequencies below 5 kHz. Then we have the duty cycle. The duty cycle is the percentage of time in which we have an on state or high state. This is measured as a percentage from 0 to 100%. Then we have the amplitude, which is the voltage of the signal. The amplitude will be in play of the effective voltage, where we multiply the amplitude times the duty cycle. If we have an amplitude of 5 volts and a duty cycle of 50%, then we have an effective voltage of 2.5 volts. Why did the PWM become so important? As we mentioned before, it's a thing of practicality and efficiency. In terms of practicality, more specific to digital electronics, generating a PWM signal is very easy for any microcontroller, because we only need a timing parameter. So it's the closest thing to analog control with only the digital resources. For the case of efficiency, this is more of a complex thing. In linear control, we vary the internal resistance of a semiconductor like a transistor. This becomes very inefficient because to reduce the power of a load, we also have to increase the resistance of the transistor, which means in power dissipated as heat. But for the case of PWM, instead of controlling the resistance, we only control the time in which a load is on. With this, we have a transistor with the lowest on resistance and we get the lowest dissipated power. Now that we have seen the theory, let's go to the lab. Do you have a project that needs to be finished? Do you have an idea for a product and you want to take it to the next level? We are your best choice. In prismacmnetwork, we have the best team to do so. We offer services on hardware design and software design. From PCB development, firmware development, app development, and desktop development. We offer competitive prices and an excellent service. Contact us to get a quote. All of the info available at the video description. We can see in this video that we have the signal shown in the oscilloscope. We have a stable frequency which is 10 kHz, but we can control the duty cycle of the signal with the controls of the function generator. We can see that we can go up to 100% and then go down to practically 0 or off state. This is obviously a digital method of generating PWM. We have also analog methods, but those will be seen further in the video. First, we have to understand how the duty cycle is shown in the signal, which is the on and off relation state. In this screenshot, we have the measurements of the signal provided by the function generator. We have the frequency operation, which is 10 kHz. We have other measurements, such as the total duration of the signal, which is 100.8 microseconds, which equates to 10 kHz. And then we have other measurements, such as the amplitude, which is 5.64 volts. And we can see that we have a very even 50% duty cycle, which means the on state has the same duration as the off state. And now, to prove the PWM efficiency, we're going to compare it with linear control. We will do a test and compare both results and see which is the best option for which case. For the case of PWM, we will do the test with the following parameters: a transistor model tip 31C, a signal of 10 kHz, and an amplitude of 5 volts. Okay, for this first test, we have the PWM control. We have the PWM signal to the left and the multimeters to the right to show the current flowing through the transistor and the temperature of the transistor. We are going to change the duty cycle and we are going to see that even though the current flowing through the transistor changes, the temperature will stay relatively the same, within 10 degrees of change at most. So we can see that the PWM signal is providing a more efficient way of controlling the transistor, because we are reaching the amplitude of activation within the transistor, and we are not varying its resistance. We're only turning it off and on, and that's it. We can see that the temperature is staying within the 30-degree range. We have a 50% duty cycle. We can lower it. We obviously lower the current, but the temperature is still the same. So this is going to be a big contrast with the next test, which is going to be a linear control. But we have to keep this image of how the temperature stayed the same, even though the current changed because of the PWM duty cycle. And now we're going to test the same conditions, but now with linear control, which is a linear voltage applied to the base of the transistor. As we can see, we already have a higher temperature of operation. We are going to lower the current flowing through the transistor. As we can see, we are right now at 1 amp, but we are going lower. And as we go lower, we can see that the temperature is rising. This is because we are drastically increasing the resistance of the transistor, which is going to mean a higher power dissipated as heat. We are reaching the 100 degrees, which is already very dangerous for the transistor. And if we go again to the lower resistance of the transistor, we're going to find that the temperature stabilizes and lowers down a bit. But as we increase the resistance again, the temperature is going to rise again. So we can see how inefficient it is. Well, at last we have to see how to generate a PWM signal. We have many ways to generate a PWM signal, both analog and digital. For the analog case, we have the option of using a timer, any 555. Using a modified version of the stable circuit, we can generate a PWM signal. Let's see it working. So now we have the 555 timer circuit to generate PWM, which is to the right, and we can see how we can change the duty cycle of the signal. Because of the nature of the components, it's not going to be very stable. I mean, it can be quite useful for many cases, but it's not stable or as stable as it can be with a digital method. We have our limitants like the minimum duty cycle and the maximum duty cycle, but it's what it is. As we could see in the video, it's relatively easy to generate PWM with an analog method, but not without some issues. First is that the output signal will be less stable with an analog method than with a digital one. This is due to many cases such as supply variations, capacitance variations, and other tolerances. Also, getting a duty cycle of 0 or above 99% will be not possible. So, the control will be far more difficult in this case in terms of stability and functionality. But we also have the capability of generating a PWM signal with a digital method. Here we have the option of using microcontrollers, with the advantage of being programmable devices. We have an almost infinite amount of options and arrays that we can create for our needs. How can we generate a PWM signal with a microcontroller? In the case of microcontrollers, most of them have a peripheral of PWM. When microcontrollers have this peripheral, it's very easy to generate a PWM signal, because we only need to manipulate the registers of the peripheral and we have an output. For this case, we will use the microcontroller Atmega 4809 that has a 16-bit timer and allows us to generate an accurate PWM signal. So here we have the PWM being generated by a digital method, which is the Atmega microcontroller. I made a code to keep increasing the duty cycle until it reaches the maximum and goes to the lower again. We can see that we have a more stable and better looking signal, or at least a signal that is more proper to many cases where PWM is required. This is a very simple code to generate, but we can apply it to many cases to find many useful applications. So PWM it's best applied when it's generated by a digital method. And now we can see an application of converting the PWM signal to a linear voltage signal. Applying a low pass filter, we can filter the low frequency, which is going to be a linear signal, technically linear, and we can see how it is now a linear signal in the oscilloscope. So we can have the PWM as a DAC, for example, or to control any linear application. So now we have the capability of linear output with a microcontroller. Well, to conclude with the video, we must understand that the PWM technique is essential to electronics for many cases, from load control to digital to analog conversion. If you are new to electronics, this is something you should learn and apply properly.